very happy that so many people have joined and so many people from outside Stellenbosch as well. So yeah, let's just jump right into it. Me, Aaron, and Ralph are going to swap between the questions and just explain how we did it. It might be a bit different from how the memo gives it, but at least we got to the correct answer in the end. So the process might be different, but the answer is at least the same. Feel free to ask any questions. We will be going quite fast because it is a lot of questions and we have limited time, but yes, so let's just get right into that. So question 1, we have this here. We are given a polynomial and we're told that P is an inflection point, and then what we're asked is what is the slope of the tangent line at point P. So can I just ask, is the quality of the camera all right? Can everyone make out what is written here?
Yeah, it looks good.
Yeah, it's pretty clear.
Great, okay. So they asked what the tangent at the point P is. So since P is an inflection point, that means that the second derivative of y is equal to 0. So we just want to find the x coordinate of this. Now, the second derivative happens to be 6x minus 6, which implies that x is equal to 1. And what they were asked is what is the slope of the tangent. So that is, they're asking what is the first derivative of y when we plug in this x. Now, the first derivative of y is 3x squared minus 6x plus 20, plus 2020. And if we plug in 1, this is going to equal 2017, which is the correct answer. Yeah.
Okay, so I'm doing question 2, and question 2 refers to this equation. It says log base 4 of x all squared equals log base 4 of x squared. Now, the first thing we notice here is we can use one of our log laws, because log base 4 of x squared is the same thing as 2 log base 4 of x. Now, if we look at this equation here, we see that log base 4 of x appears on both sides. So this is actually a quadratic equation in log base 4 of x. It might help you if you let y equal that. Might make it a bit clearer. Then this is just the equation y squared equals 2y. And this is an equation we know how to solve. We can just take everything to the one side, factor it, and that leaves us with y equals 0 or y minus 2 equals 0, which happens if y equals 2. Then we can substitute back for y as log base 4 of x. So log base 4 of x is 0, or log base 4 of x is 2. And then just using the definition of logs, this means that x is 4 to the 0, or x is 4 squared. 4 squared is 16, and 4 to the 0 is 1. Now, the question asks, what is the sum of the two solutions? So the sum is going to be 1 plus 16, which is 17. So our final answer for this question is 17.
So third question was f of x is 1, 2, 3, 4 over 5 plus e to the x. So we want to find the f. So for any e to the x, we have that this is in the range from 0 to infinity. So e to the x plus 5 is in the range from 5 to infinity, which means that 1, 2, 3, 4 over 5 plus e to the x will be in the range of 1, 2, 3, 4 over infinity, which is 0, up to 1, 2, 3, 4 over 5. And this is 2, 4, 6, 8. So the integers in the range is all of them from 1 up to 246, so 246 is the answer.
Okay, cool. So question 4 is the truth and lie tellers problem. And it's got two people, Jack and Jill. And it tells you for each day of the week whether they tell lies or they tell the truth. So it says Jack tells the truth on Mondays, Tuesdays, Wednesdays, and Thursdays, and Jill tells the truth on Friday, Saturday, Sunday, and Monday. And then it tells us that on some day, both of them say, yesterday I told lies. So we need to ask ourselves, when is it possible that one of these people would say, yesterday I told lies? Well, it's possible that they are telling the truth, and yesterday they did indeed tell lies. So that would be all the days when they're telling the truth today and not telling the truth yesterday. So that's when they have a tick next to them, but don't have a tick the previous day. So for Jack, this happens on Monday. He's telling the truth, but on the previous Sunday, he wasn't. For Jill, this happens on Friday. She was telling the truth, but on the Thursday, she wasn't. The other option is that they could be lying when they say this, which means today they're telling lies, but yesterday they were actually telling the truth. So for Jack, this happens on Fridays. He tells lies on Fridays, but the day before he was telling the truth. And this happens for Jill on Tuesdays. She tells lies on Tuesdays, but the day before she was actually telling the truth. So we can see that for Jack, the days where he tells the truth, and then the days where this is possible for him is Mondays and Fridays. And for Jill, the days where this is possible for her are Tuesdays and Fridays. And so the only day where it's possible for both of them to say this is Friday. So our final answer is going to be Friday.
Great, thank you. So next question is question 5. Fabi has a polynomial px, and we are given that this is true, and then we are asked to find p5. So what we're going to do is we're going to say px is equal to some coefficient a, x squared, plus bx, plus c. Then it follows that the first derivative is going to be 2ax plus b, and the second derivative is going to be just 2a. Now, considering the powers of x, when we add these up, it needs to get to 20x squared plus 20. So since the only x squared is here, that means that a is equal to 20. There's no x to the power 1, so that means that bx plus 2ax needs to equal 0. Now 2ax we know is 40, so b is equal to minus 40. And finally, we have here for just the constant, we have that 20 should equal c plus b plus 2a. Now 2a is 40, b is minus 40, so c must equal 20. So now we have the coefficients of our polynomial. If we now put in p5, that's going to be 20 times 25, which is going to be 500, minus 40 times 5, which is going to be minus 200, and then finally c, which is 20, plus 20. That gets us to 320, and that's our final answer.
Okay, cool. So for question 6, we have this polynomial 1 plus 2x plus 3x squared plus 4x cubed plus 5x to the 4, and all of this raised to the 6th power. And the question is to find the coefficient of x squared in this expansion. So if we think about expanding this, we'll realize that each term in the resulting polynomial is going to come from choosing one of the 6 terms 6 times and multiplying them together. So because that's how multiplication works. You can think of FOIL or extended FOIL. So then we ask ourselves, how can we do this in such a way that what we're left with is going to be an x squared? Well, we can't ever choose this 4x cubed or this 5x to the 4, because our power of x is already too big, and multiplying it by something else isn't going to make it smaller. So we don't have to worry about these terms. If we choose a 3x squared, then we've already got an x squared. So we can't have any more x's, which means that we'll have to choose this 1 all of the other times. So, and how many ways are there to do this? Well, we'll have to pick one of the 6 brackets to choose the 3x squared from. And the number of ways that can be done is 6 choose 1, the binomial coefficient. And what's that going to leave us with? We'll have to choose the 3x squared once and the 1 5 times. And this is going to be 6 times 3x squared, which is 18x squared. The other way we can do it would be, well, we said we can only choose this once, so the other alternative would be never choosing it. Well, that means we'd have to choose this 2x twice, which can be done in 6 choose 2 ways. And then in each of those 2 ways, we'll be choosing the 2x. And then for each of the other ways, we'll be choosing the 1. Now 6 choose 2 is 6 times 5 over 2, which is 30 over 2, which is 15. 2x all squared is 4x squared, and that's just 1. So this gives us 60x squared. So in case 1, we had 18. In case 2, we had 60. So our final answer is going to be 18x squared plus 60x squared, which is 78x squared. And we're asked for the coefficient of x squared, so the answer is 78.
Great. So next is question 7. So we were given that there's an unfair coin, and we're given that getting 2 heads and 2 tails in any order has the same probability as getting 1 head and 3 tails in any order. And then we're asked, what is the probability of getting a heads in any flip? So let's just set the probability of getting a heads to P. So we want to find P. Now, what we then need to use is the binomial theorem. So from 2 heads, 2 tails, we get 4 choose 2 positions for where the 2 heads could be. And that's P squared and 1 minus P squared. Of course, we're canceling out the part where it lands on its side, because that's not how mathematics works. Mathematics doesn't allow that. And then here, we're choosing 4 choose 1, just P, and 1 minus P cubed. Of course, this is going to be 6, and that's going to be 4. Taking everything to one side, expanding, and then looking what we get, this gets us to 10p to the power 4 minus 24p cubed plus 18p squared minus 4p equals 0. This factorizes towards 2p, p minus 1 squared, and 5p minus 2 is equal to 0. In this case, p has 0 probability, which we don't want, because then it's basically not a coin, it's 100% chance for tails. And here p has 1, so it's 100% chance for heads. Both of these we don't desire really. So all that's left is this. So then p is equal to 2 over 5, which can be seen as a 40% chance at any point to get a heads.
Okay, my next question is this question 8. So we have this function f, which is given to be differentiable, and a is defined as so, and b is defined as so, and we have some more information. Okay, so the first thing to notice is that there's an x, a 2x, and a 4x over there. So we can try and get rid of that 4x potentially by exploiting that a of 2x would be f of 2x minus f of 4x. And we were given that b of x is f of x minus f of 4x. So if we take the difference between these two things, we get that b of x minus a of 2x is f of x minus f of 2x, which is just a of x by definition. So b of x is a of x plus a of 2x. So now if we take the derivative of b with respect to x, we can just take the derivatives over here and use the chain rule that we get that this is true. And now plugging in that x is equal to 1, we get that b prime of 1 is a prime of 1 plus 2a prime of 2. And we were given that this is 10 and this is 11. So b prime of 1 is 10 plus 2 times 11, which is 32.
Okay, thanks. So for question 9, they've given us 3 points. The first is 2xy, the second is x3y, and the third is xy7. So those would be the x, y, and z coordinates respectively. And we're told that these 3 points are collinear, and we have to find x plus y. So if we look at the x coordinates, we see here we have an x coordinate of 2, here we have an x coordinate of x, and here we also have an x coordinate of x. So the x coordinate is repeated, but these 3 points lie on a line. And if you think about how a line works, if your line is sloped, then once you leave a particular x coordinate, you can never really come back to it. So the only way we can have 2 points on the same line with the same x coordinate is, in fact, if that line never leaves the x coordinate. So it's a straight vertical line. So that means the x coordinate is constant, which means, in fact, all 3 of these have to be the same, which means that x is 2. And we can do a similar thing with the z coordinates. We look here, we see these 2 z coordinates are both y, but this z coordinate is 7. We can't have that 2 z coordinates are the same unless all the z coordinates are the same. So that means that y is actually equal to 7. So it turns out these points are 227, 237, and 277. But the answer to the question, x equals 2, y equals 7, which means that x plus y equals 9. So the answer to our question is 9.
Okay. Next question is this lovely limit over here. So the way that I approach this is to notice that I know that this is n times n plus 1 over 2. That's just the sum of all positive integers up to n, which is a half n squared plus something. Then if you do the same thing but with squared terms, you get n times n plus 1 times 2n plus 1 over 6, which is a third n cubed plus something. And for the case with cubes, we have it's, well, it's just this thing squared, which will turn out to be 1 over 4 into the 4 plus something. So you can hypothesize that 1 to the k plus whatever up to n to the k will be 1 over k plus 1, n to the k plus 1 plus something. And you can prove this by looking at the integral of this function f of x equals x to the k, and you'll see that it will be of that form. So this means that the limit as n goes to infinity of 1 plus 2 is n, minus 1 to the 8 up to n to the 8 over cubed plus cubed and 1 to 6 up to n to the 6 will just be the limit as n goes to infinity of 1 over 2 n squared times 1 over 9 n to the 9 over 1 over 4 n to the 4 plus times rather 1 over 7 n to the 7, because those terms will dominate the expression. And now we have the degree at the top is the same as the degree at the bottom, so we can cancel out the n terms, and we are left with 1 over 18 over 1 over 28, which is 28 over 18, which is 14 over 9, which is the correct answer. Okay, I'll be doing the next question as well. So that given f of x is this thing, find this other limit. So after looking at it for a bit, you realize that finding this inverse function is going to be a real pain, so that's probably not the best way to go about it. So instead, what we'll do is we'll say, okay, let some u be this inverse. Okay, now what we know about u? Well, f of u is just f of the inverse of 27x, which by definition is just 27x. But also we have that this is 8u cubed plus 5u by the definition of f. So this must be equal to this. So that means that 8u cubed plus 5u is equal to 27x, or alternatively x is 8 over 27u cubed plus 5 over 27u. Okay, now going back to the original expression, it was the limit as x goes to infinity of x inverse 27 of x over x to the power of 1 over 3. And substituting in u values, we have the limit, the numerator is u, and the denominator is 8 over 27 u cubed plus 5 over 27 u, or to the 1 over 3. And now, since f was given as 8 x cubed plus 5x, this is an increasing function beyond some point, because it's a polynomial with odd degree and a positive leading coefficient. So that means that as x goes to infinity, u also goes to infinity. So over here in the limit, we have this is as u goes to infinity. Okay, and now from here, we can factorize u at the numerator and denominator and get that this is the limit as u goes to infinity of 1 over 8 over 27 times 1 plus 5 over 27 u to the minus 2 to the 1 over 3. Okay, and as u goes to infinity, that term vanishes. So we're left with 1 over 8 over 27 to the power of 1 over 3, which is 1 over 2 over 3, which is 3 over 2. Okay, I'll be doing the next one as well. So v and w are two complex numbers with these properties. So the important thing to realize here is that we don't particularly care about the phase of v and w when you look at them as vectors in the complex plane. So what we can do, given that magnitude of v is 2, we can just arbitrarily decide, okay, well, let's just say that v is 2. This will be our reference. And then since magnitude of w is 3, we can say that w is 3 times the real part, which is cos of some theta plus 3I times the sine of some theta, where theta is the phase of it. Okay, we were given that the magnitude of v plus w is equal to 4. So this is equivalent to the magnitude of v plus w squared is equal to 16. Okay, and if we work this out in a different form, we get that this is 2 plus 3 cos theta squared plus 3 the sine theta squared is equal to 16. If you just look at the real component squared plus the complex component squared. So expanding this, we get 4 plus 12 cos theta plus 9 cos squared theta plus 9 sine squared theta is 16. So we have the cos squared and sine squared together, that's just 1. So 12 cos theta is equal to 3. Yeah, 3. 16 minus 4 minus 9 equals 3. So cos theta is 1 over 4. Okay. We want to find v minus w's magnitude. So the square of that is just 2 minus 3 cos theta squared plus minus 3 sine theta squared. And we'll get almost exactly the same expression, plus 9 cos squared theta plus 9 sine squared theta. The only difference is this is a minus where it was a plus before. So we can rewrite this as 16 minus 24 times cos theta, which is 16 minus 24 times 1 over 4. And this is 6, so we end up with 10. And therefore, the magnitude of the difference is the square root of 10.
Great, thank you, Ralph. So the next question, we were given these 3 graphs. I just differentiated between the y's by saying that y subscript plus is where y goes to infinity, y subscript minus is where it goes to negative infinity, and y subscript circle is the circle. And we are asked to find a for some a larger than 0. So what we notice is that if we take the derivative of 2 of the y's and we set them equal to each other, that's going to represent one of the tangents here, or here, or there, or there. So that's very useful to us. So I'm going to focus only on the y plus and the y0. So these 2 points over here. So the derivative of y plus is equal to 2x, and moving this about, y squared is equal to 1 minus x squared. Square rooting that gets us 1 minus x squared. I'm just going to stick to the positive. I'm going to ignore the plus minus. And then the derivative of this is going to be 2, 1 minus x squared minus 2x. 2's cancel out. And to get these 2 points, that's where we set that derivative equal to this derivative. So 2x equal to that. Now, setting that equal to each other, multiplying by the square root 1 minus x squared, and simplifying it out, we eventually find that x is equal to plus minus square root 3 over 2. The plus just refers to this coordinate here, and the minus only refers to this coordinate here. Now, putting this back into our circle graph, we can find what y0 is. So putting this in, x squared is going to be, that's going to be 3, like that, plus y0 squared is equal to 1. So that needs to equal, no, wait, sorry, that's 4. That needs to equal a quarter. So this implies that y squared, y is equal to plus minus a half. But it needs to be minus a half because we're looking at these 2 points. It's below the x-axis. So we're only interested in minus a half. So since the derivatives are equal to each other, we can say that they are actually also equal to each other. Y0 is equal to y plus. And putting this back in there, we then get that minus a half is equal to x squared. That's going to be 3/4 minus a, which implies that a, moving it over and all of that, gets us 5/4. Final answer.
So question 14, we were talking about functions from the set 1, 2, 3, 4, 5 to itself. And the question was, how many of these functions take on exactly 3 distinct values? So when you have a hard problem like this, it's often easier to break it up into simpler problems to try and get a feel for it. And often those problems will help you in the solution. So let's say instead of exactly 3 values, we had exactly 1 value. How many such functions would there be then? Well, let's say they all had to map to some number a. Well, then we'd know f of 1 would be a, f of 2 would be a, and so on up to f of 5. So for some particular value, there'd only be 1 such function. Of course, we'd have to multiply by 5 because this a could be any of 1, 2, 3, 4, or 5. So this would correspond to the case where everything maps to 1, everything maps to 2, etc. So this is the case where we only have 1 value. What if we had 2 values? Well, then let's say everything is mapped to the set AB. Then f of 1, there are 2 possible choices. It could be A or B. F of 2, there are also 2 possible choices. F of 3, still 2 possible choices, 2 choices for f of 4, and 2 choices for f of 5. So this would be 2 to the 5, which is 32. But this isn't our final answer because some of these 32 cases won't have exactly 2 values in the range. One of these cases will be where everything is mapped to A, so we'd only have 1 value. Another case would be where everything is mapped to B. Then again, we'd only have 1 value. So we have to subtract those 2 cases. All the other cases will have at least 1 A and at least 1 B, so there'll be 2 values in the range. So the answer, if the question said how many functions take on 2 values, would be 2 to the 5 minus 2, which is 30. And again, we'd have to multiply by 5 choose 2, because there are 5 choose 2 ways that we could choose these initial values, A and B. So now we're equipped to tackle the actual question, which is when you've got 3 values, A, B, and C. Okay, so how many functions are there now? Well, there are 3 possibilities for f of 1, 3 possibilities for f of 2, 3 possibilities for f of 3, 3 possibilities for f of 4, and 3 possibilities for f of 5. So this is 3 to the 5, which is 243. But like we did for the previous case, we need to subtract some things. We need to subtract the cases where we don't use C at all. We only use A and B. Well, there would be 30 of those because we just said there are 30 there. We also need to subtract the cases where we don't use A. We just use B and C. So that's another 30. And we'd also need to subtract the cases where we don't use B. We just use A and C. So that's a third 30. So we need to subtract 30 times 3. So now we've subtracted the cases where we use exactly 2 values. All that's left is to subtract the cases where we use exactly 1 value. So there's going to be 1 case where we only use A, 1 case where we only use B, and 1 case where we only use C, because we saw that the answer was 1 there. So that's minus 3 times 1. So this is going to be 243 minus 90 minus 3, which is going to be 150. Now that's not our final answer, because this is just the answer for some specific choosing of A, B, and C. We can choose A, B, and C freely from this range 1, 2, 3, 4, 5, and we can choose it in 5 choose 3 ways. So our final answer is going to be 5 choose 3 times 150. If we compute 5 choose 3, we'd see it's 5 times 4 times 3 over 3 times 2 times 1. 3's cancel, that becomes a 2, and the answer will be 10 times 150. So our final answer is 1,500.
Calculated. Because you have to decide which.
Okay, so now we're going to look at question 15. And question 15 asked us to find the minimum value of this expression. It was xy squared plus x plus 7 squared plus 2y plus 7 squared. Now, hopefully we all know that any square number cannot be negative. This is because positive times positive is positive, negative times negative is also positive. So all squares are non-negative. We could write that as a squared is greater than or equal to 0. So immediately we can see that no matter what we plug in for x and y, this part's going to be greater than 0, this part's going to be greater than or equal to 0, and they're all going to be greater than or equal to 0. So we know that it can't be less than 0. But we would also see that it can't be equal to 0 because there's no combination of x and y that are going to make all of these 3 brackets 0. And that's because we only have 2 variables to play with, but we have 3 brackets. If we only had 2 brackets, then we could find some combination that would work. So we need to find some way of reducing these 3 squares into just 2 squares. And then we can do something like what I've outlined above. So let's expand these squares and see what we get. We have x squared y squared, x squared plus 14x plus 49. We have 4y squared, and that's a 9. 4y squared plus 28y plus 49. Now, if we look at the terms here, we have an x squared. So if we're going to square something, it should probably have an x in it. We've got 4y squared, so again, it should probably have a 2y in it. And we also need to make this 14x and this 28y somehow. We know 14x is 2 times x times 7, and 28y is 2 times 2y times 7. So if we add a 7 here, that will knock both of those out in one go. So if we evaluate x plus 2y plus 7 all squared, we'd get x squared plus 4y squared plus 49, that's just squaring the individual terms, plus 2 times x times 2y, which is 4xy, 2 times 2y times 7, which is 28y, and 2 times x times 7, which is 14y. And we see that what we have in the red expression and what we have in this black expression here actually have a fair number of common terms. The x squared is common, the 4y squared is common, the 49 is common, the 28y is common, and the 14, that should be an x, sorry, the 14x is common. So, but what we have here that we didn't have before is a 4xy. So because we added 4xy, to compensate, we're going to have to subtract 4xy. And of course, the 2 terms we didn't use are just going to stay there. We're going to have an x squared y squared, and we're going to have a 49. So now we've made one square. How can we make another square? Well, x squared y squared is xy all squared. And if we try to like complete the square here, since we have xy all squared and minus 4xy, we'd see that this is almost the same as xy minus 2 squared. Of course, the difference here, we'd have an x squared y squared, we'd have a minus 4xy like we did above, but we'd also have a plus 4. So to compensate, because those will cancel and those will cancel, so to compensate, we'll have to subtract 4. And again, we'll have our plus 49, and we'll have our plus x plus 2y plus 7 squared. So just neatening this up a bit, this is xy minus 2 squared plus x plus 2y plus 7 squared plus 45. So now we can indeed use the argument that I used earlier. We know that since this is a square, it's greater than or equal to 0. Since this is a square, it's greater than or equal to 0, and this is 45. So we know our entire expression is greater than or equal to 45. The only question is, are we still going to suffer the same problem as before? Is there still going to be no way that we can assign x and y such that these two conditions will hold? Well, let's find out. We could say that if this is going to be 0, then that means xy minus 2 would have to be 0. So xy would have to be 2. In other words, y would have to be 2 over x. For this to be 0, we'd need x plus 2y plus 7 equals 0. And we know y is 2 over x. So x plus 2 times 2 over x is 4 over x plus 7 equals 0. We can multiply it through by x to get x squared plus 7x plus 4 equals 0. So just to check, does this quadratic have any solutions? Well, we could plug into the quadratic formula, but since we don't really need to know the actual solutions, we just need to know, do they exist? We can just check the discriminant, right? Delta, which is b squared minus 4ac, which in this case is 49 minus 4 times 1 times 4, which is 33. And this is greater than 0, which means, in fact, yes, solutions do exist to this quadratic equation, 2 of them, in fact. We can find them explicitly by plugging into the quadratic formula, but for the purposes of this question, we don't need to. We know there are values that will make this 0 and will make this 0, and so we'll make the whole thing 45. So our answer to this question is 45. Okay, so now we can move on to question 16. Question 16 asks us to determine integral from 0 to 2020 pi, and it will be of the minimum of, oh, sorry, that should be a pi. The minimum of sine x and 0 with respect to x. So if we look at the graph of sine of x, we see it starts at 0 and it just does our classic sine wave, where this is pi, this is 2 pi, 3 pi, 4 pi, etc. So then when are we going to have that our integral we're interested in is actually sine x, and when is it going to be 0? Well, from 0 to pi, the minimum is 0 because sine of x is above 0. From pi to 2 pi, the minimum is sine of x because sine of x is below 0. And then it just repeats. We go 0, sine of x, 0, sine of x. And since we're interested in the area under this curve, we know that in all these flat components, the area is obviously 0. So we just need to find the area in these components. And how many components are there? Well, the first one goes up to 2 pi, the second one goes up to 4 pi, the last one goes up to 2020 pi. So there's going to be a total of 2020 pi over 2 pi, which is 1,010 components. And then we just need to find the area in one of these components. So our final answer is going to be 1,010 times the integral. So from here we're going pi to 2 pi, sine of x dx. Okay, now we know the derivative of cos is minus sine, so the derivative of minus cos is sine, the integral of sine is minus cos. So this is going to be minus cos of x evaluated at pi and 2 pi. So our final answer is going to be 1,010 times minus cos of pi, minus minus, which is a plus, minus cos of 2 pi, minus minus, which is a plus, cos of pi. Cos of 2 pi is just cos of 0, which is 1. So that part's going to be -1. And cos of pi is -1. So our final answer is going to be 1010 times -2. So the answer is -2020. And that's our final answer for this problem.
Great, thank you, Aaron. How do I top this about? Great. So next is question 17. Question 17 asked us to find for some matrix A, which is n by n, how many such A's can exist such that all the entries are either 0 or 1. All the entries in its inverse are 0 and 1, and since it has an inverse, that means that A needs to be invertible. So the approach that I took was starting with small examples, say where n is equal to 2, and then trying to find a pattern and using an induction hypothesis to assume what the answer would be for some general n. So for 2, we know that the identity is one example. It is invertible. And we also know that that one is an example because its inverse is just going to be itself. So we know that there's at least 2 cases. Now, if we were to remove one of the ones, it would not be invertible anymore. And if we were to add 1 towards one of the 0 spots to replace the zeros with a 1, say we were to take 1, 1, 1, 0, we would find that its inverse is going to be 1 minus 1, 1, 0. And -1 is not allowed, so this does not work. And we find it true if we put it in that 0, or that 0. So for n equal to 2, it's going to be 2 such A's. If we were to take n is equal to 3, now we have a bigger matrix, we would find that it is still the case, or we would find that if we just were to put n amounts of 1 such that each row and each column has at least a 1 in it. So say we were to take this matrix here. We find that this is also an example, and if we were to try and calculate its inverse is just going to be it as well. Its inverse is going to be itself. And this suffices. And then we start thinking maybe it's possible that for all n, this would always be the case, that if we just were to have n amounts of 1 and exactly one of them in each row and each column, then it would work. And we find that this is in fact the case. If we were to say have some n by n matrix and say we have say have 1 there and we have 1 there, and then somewhere way down the line we have a 1 there and so on, its inverse is just going to be taking the matrix with all its entries and just flipping it like that. So for example here, if you were to flip A like that, it's just going to be itself and that's it. Same was true for this and same was true for the identity. So we know that there is at least then n factorial cases, because that's how many permutations there are to place all the ones in n by n. So say, for example, we have n by n. In the first column, there are n spots where we can put a 1. So say we put a 1 here. For the second column, there's n minus 1 spots that we can put the 1 because we can't put it here anymore. So n minus 1 for that one, and then n minus 2 and so forth. And this is just going to be n factorial. Now, what we still need to check is, are there any cases that we are still missing? So using the same example that we used here and just on a bigger scale, we find that there in fact aren't any others. If we were to have any matrix, say with a bunch of 1 entries in some places, and say we were to have in some row, we were to have 2 1s, this would not be, this would be invertible because we still have a 1 in each row, but finding its inverse, we would find that the 1 would be a -1 in the inverse, which is not allowed by our requirements. So in fact, the answer is just going to be n factorial.
Okay, the next one is question 18. So you have this curve, which is defined by x is ln t plus 2 and y is 1 over t plus 1, where t is in that range, and we want to find the area between the curve and the x-axis. So the first step is to realize that essentially what's being asked is to find the integral of y dx from t equals 1 up to t equals 2. Okay, so if we just plug it in as is, we get that it's integral from 1 to 2 of 1 over t plus 1 d ln t plus 2. And this doesn't really help us at all. So let's try and rearrange it a little bit. So we're given that x is ln of t plus 2, which is the same as saying that e to the x is just t plus 2. So t is e to the x minus 2. Okay, and we're given that y is 1 over t plus 1, but we can find, or we know what t is in terms of x, so if we plug that in, we get that it's 1 over e to the x minus 1. Okay, so going back to what we originally had to find, we now have y completely in terms of x, so we can try and evaluate this integral. So we have the integral of 1 over e to the x minus 1 dx. And when we transformed from x in terms of t to t in terms of x, we need to change the bound as well. So when t equals 1, we have ln 3 over here. So the lower bound is ln 3. And when t equals 2, x is ln 4. So the upper bound is ln 4. Okay, so this looks a lot more approachable than the previous one. So now you notice that we can get rid of this e to the x by saying let u be equal to e to the x. Okay, in that case, we get that du would be, well, the derivative of this, which is just e to the x times dx. Okay, but we know that e to the x is just u, so this is just u dx. So in fact, we have that this dx is 1 over u du. So putting that back into the original expression, we get the integral from 1 over e to the x is just u, so u minus 1, and dx is 1 over u du. Okay, and now again, we have to look at our bounds. So when x is ln 3, then e to the x is 3, and when x is ln 4, e to the x is 4. So this is now our new integral, which looks even easier or more approachable. So we can rewrite this as the integral from 3 to 4 of 1 over u minus 1 minus 1 over u du. And you can see this just from partial fractions that the u's get cancelled out and you're left with the 1, the numerator, and u minus 1 times u, the denominator. Okay, and we know how to do integrals of this form. because this will just be ln of the absolute value of u minus 1 minus ln of the absolute value of u plus c from 3 to 4. Okay, so this is then the ln of 4 minus 1, which is 3, minus the ln of 4, minus the ln of 3 minus 1, which is 2, minus the ln of 3. And tidying up a bit, we get this is 2 ln 3 minus ln 4 minus ln 2. And well, 4 is just 2 squared, so we have that ln of 4 is 2 ln 2. So this whole thing is 2 ln 3 minus 3 ln 2, or just ln of 9 over 8, if you prefer that.
Great, thank you. So now we're on question 19. So question 19, apologies for the beeping, load shedding just started here. Question 19 says we have a 20 by 20 grid, and we need to color each tile with colors such that each row and column has at most 7 colors. So again, much like question 17, I used an inductive argument. So I started by saying, okay, if we just had 2 colors, how many ways are there of doing this? So say I'm going to use numbers to denote colors. Say we put a color there, then everything else in this row and column can be either colored 1 or some other color. But this row and this column just above and next to it is unaffected by this 1. So we can put a different color here. We can put 2 there, and then the same goes there. So it's 3, 4, 5. And we can continue like this, and we can put 19 there and 20 there. And then we can then see that, okay, well, we can't put 1s here or there because it will then affect 2 and 3, and then it will fill up their columns, and then we'd be stuck with 20. But if we make all the rest the same color, say color 21, so 21 populates all of these, then we're going to have 21 colors. And I think it's pretty simple to see why this is the maximum case for 2 colors. So for 2 colors, we have 21. Now, if we were to now move to 3 colors, what would be the case then? So with 3 colors, if we try and now, okay, let's just remove that just for conveniency. We'll rename it a different number in a moment. Say we were to put a 21 color there now. Now the same follows here. In this column and in this row, we can now color all the rest our usual color that we used to call 21. We can color it like that, and we can continue like this because again, this column and this row is unaffected by this 21. So we can say 22, 23, and we can continue like this, and we'll get 39 there. And then we can jump down here because this column and this row is still unaffected by the new entries, and we can put color number 40 there. And then by the same method, we can call all the rest that are not filled in color number 41. So then for 3 colors, we get there's 41. So we are kind of getting this idea that it's going to be the amount of colors, so n minus 1 times 20 plus 1. So 20 times 1 plus 1, and 20 times 2 plus 1. So now for 7 colors, let's see what we get. So we're going to fill in here. We're going to have a color number 41 there, and we're going to populate it so on, and we're going to have a 59 here and 60 there, and then a 61 there, and so on. So by the same method, 7 colors is then going to give us 7 minus 1 times 20 plus 1, which is going to be 121. And that's our final answer.
Okay. For the last question, we have that x is some irrational number, and it satisfies that x squared minus 2x is rational and x cubed minus 8x is rational, and we're tasked with finding all such x. Okay, so we start by noticing that if x squared minus 2x is equal to some p over q, where p over q is just some rational number, then all solutions to this equation must be of the form x is a plus or minus the square root of b, where a and b are both rational numbers and b is restricted to being positive. Okay, and you can see that just from looking at the quadratic formula when you have rational terms as coefficients. Okay, so we'll assume that x is a plus or minus the square root of b for those values. So plugging that into this, we get a plus or minus the square root of b squared minus 2 times a plus or minus the square root of b has to be rational. So this is just a squared plus or minus 2a square root of b plus b. So when you square this term, the plus and minus gets cancelled out. And here we have this minus plus 2 square root of b. Notes that the order of these two changes because of the minus in front. So grouping terms together, we know that a squared plus b minus 2a is a rational number. So if this whole sum is rational, and we know that this is rational, then we must have that plus or minus 2a square root of b minus plus 2 square root of b must also be a rational number. Okay, we can factor out the square root of b over here. So we get the square root of b times plus minus 2a minus plus 2. Okay, so this must be a rational number. And we're told, well, we're assuming that this b is a positive value, which means the square root of b is non-zero, which also means that this square root of b must be irrational. So that means the only way to get a rational number times an irrational number back to a rational number is if this term is 0. So we have that plus minus 2a minus plus 2 must be equal to 0. And this is just equivalent to 2a minus 2 is equal to 0, so a is equal to 1. Okay, so that gives the first term, and now I need that second term. So the second equation is x cubed minus 8x, which is going to be 1 plus or minus the square root of b to the power of 3 minus 8 times 1 plus or minus the square root of b. Okay, and if we expand this out, we get that this is 1 plus or minus 3 times the square root of b plus 3b plus or minus b times the square root of b minus 8 minus plus 8 times the square root of b. Okay, and with the same argument, we know that this is a rational number. So we group together terms. So 1 plus 3b minus 8 plus or minus 3 square root of b plus or minus b square root of b and minus plus 8 square root of b. So this is a rational number. The whole thing is a rational number, so this must also be rational. So we have that plus minus 3 square root b plus minus b square root b minus plus 8 square root b must be rational. And this is just plus minus square root of b times 3 plus b minus 8. So we know that this is rational, but the whole expression is rational, which means that this expression must be 0. So 3 plus b minus 8 is equal to 0. So b is equal to 5. And hence the only values that will work is x is equal to 1 plus or minus the square root of 5.
Great. Thanks for joining, everyone. I hope it helped clarify some problems that you might have struggled with. Are there any questions about any of the that any of you have about any of the questions or solutions that we presented? We'll give you a few seconds. Okay, great. If no one has any questions, then yeah, thank you very much, everyone, for joining. And I hope everyone has a good day and load shedding doesn't mess up your day. Great. Thank you.